as you mentioned, this is our title. And so, well, before we start discussing our actual implementation and everything, let's talk about some background information. Right, so what is reinforcement learning? So reinforcement learning is a subset of machine learning that sort of falls somewhere between supervised and unsupervised learning, right? And so basically what reinforcement learning is aiming to do is to control an agent within an environment such that it plays in a way that is optimal by some metric. And this metric actually is known as a reward. And so this reward value is something that, say, the researcher decides, right? So, for example, you have a mini game for Roomba, right? Its goal is to collect garbage, right? And you want it to, it's rewarded whenever it collects junk, but it's negatively rewarded every time it makes a mistake, like bumping into a wall or bumping into a person. So this is sort of like the idea behind what reinforcement learning is trying to do. So positive reward when the desirable task is performed, and negative reward when undesirable task is performed. And so what is the deep aspect? So the deep aspect of deep reinforcement learning is utilizing neural networks to behave as some function for the reinforcement learning algorithm. And so a brief background on neural networks. There's sort of like a theoretical model that represents, it's a machine learning theoretical structure that is a way that represents information being passed in and how information is then processed to derive an output. So essentially it's a series of linear algebra operations from input to produce some output. This is a very general description of neural networks. And so the distinction between a regular neural network and a deep neural network is rather superficial, in the sense that the only difference between a simple neural network is that it only has one hidden layer, and a deep neural network has additional hidden layers, right? And so these hidden layers, information is passed through, and there's a function known as an activation function that is applied at each layer, right? And then the output then is interpreted to represent some piece of relevant information based on input data. All right.
So we did our project within the StarCraft 2 game engine. It's a real-time strategy game, and essentially each player manages a whole set of units to build a base and play the game, fighting an enemy, usually another player. And the control of the game is about collecting resources and making sure you have enough versus your opponent. And so we designed our AI based on gathering resources and using that as our reward factor. And so we used the custom game available to us, provided by our library, the ISC2 library. And so the library is actually a set of, it's an API that actually uses another API to actually run on top of StarCraft 2. So, because StarCraft 2 is based on C. And so to run it, Blizzard designed a StarCraft 2 learning API that connects to that, but it's all written in C. And so what PySC2 does is it takes that C data and uses Python instead. So now we can control it using Python instead of writing everything in C. So it makes it a lot easier to like design the games and control our AI. And then we have the mineral collection mini game that we're using to test and train our AI. So there's 20 minerals randomly placed on the map, and it's reset every time the map is completed. And we have Marines that are controlled by the AI, and the Marines just walk around the map collecting whatever's the closest mineral to them, based on what the AI decides it wants to do. And so the game naturally ends at a minute 30, but it can actually like reset the map if it clears out the map before the game actually ends. So, here's an example of our laser. So here's our Marines here, and here's the minerals all randomly dropped on top of the map. And so the Marines would like walk. It would like the AI would randomly generate like what's next mineral I should be heading towards. And so the mineral of the Marines would then start moving towards an individual mineral as it ran through the AI.
Okay, so for the methodology, so essentially to create the AI, we actually use the PyTorch library because it just does a lot of the legwork for us, and it was pretty simple to pick up. And then once we kind of set up the basic neural network, Brandon actually works to implement the reinforce algorithm. We use that to compute the loss. Every time that it collects a mineral, we give it a +10 to its reward value. And then for every just like step in the the game, it gets a negative 0.1 reward for just standing still, really just anything that isn't getting a mineral. And then the output was eventually a vector of 21 inputs that represent the probabilities. Okay. So for the system setup, we had an NVIDIA GTX 1080 Ti graphics card. This is important to note because we were actually using CUDA to run it on the graphics card. That's where we did all of our training for it. So once it actually got up and running, we just leave that going for days on end, pretty much. And then we had the Intel i7 8700K CPU and 16 gigabytes, 3200 megahertz DDR4 RipJaws VRAM, all that good stuff. For the experiment setup, like I said, we built the AI, we implemented the reinforced algorithm, and then we used the PySE2 API to actually load it into the mineral collection minigame, and we just run it and rinse and repeat, just run it over and over and over, because when it first starts, obviously it has no idea what it's doing, it's really not that smart, but the goal is that eventually after thousands of episodes, it's gonna start to figure it out.
So, one cool thing about using a video game to train your AI is you can capture footage and actually watch it happen. So, here's an example of the AI kind of learning. And it's stuck to it, like it's still learning, so it doesn't actually know what it needs to do. It's still figuring out what is a reward, what's not a reward, and that kind of stuff. So it kind of gets stuck here, and it's in between minerals, and it's indecisive. So you kind of see that it's kind of picks a mineral, but it doesn't know exactly which one to go to. And the game timer up here is counting down pretty quick, and it's just, it spends a whole minute just saying, oh, maybe, it's just getting negative rewards all the time. It didn't learn from this random generation that well.
And that was actually like the #1 problem we had while we were training it, because anytime you get these like triangle configurations of the minerals, it just gets in the middle and freaks out because it doesn't know where to go.
Yeah, here, I'll play one more time so you can kind of watch. Oh, like it kind of gets a reward when it grabs that one, and then there's just no clear path for it to know how to get that next reward.
And so we actually generated like custom maps with like the minerals preset, and we like tested out like why was it just picking like whatever mineral? Because if you put all the minerals like in a circle formation, the AI will just sit in the middle because it was so indecisive in picking like where the heck am I going? It just kept going, getting more negative and negative, but it was never ever getting a positive.
Right.
So that's why I thought like figuring out like, oh, I should be actually going to grab a mineral now.
And like we kind of played with the idea of exploration, which is you purposefully take a move that's not the highest reward so that you can kind of not get caught in a certain train of thought. You kind of explore like, oh, we think the answer is here, but in reality it could be over there. And if you're not exploring, you'll centralize around an answer that you think is right, but there could be a more optimal answer somewhere else. And we have like possible approximations. All right, so here's another thing that kind of happens sometimes where the AI would be cruising along and then it would just stop and just stall out. And it kind of didn't make sense to us at first. Like you can kind of watch, it does pretty well. And it just, the timer goes way down and it's not even moving. It's making it like, one of the possibilities is do nothing. So that's the highest rewarded value. And then right at the end, it's just like, oh, okay, go grab the mineral. So it finally received enough negative rewards that another action of like, hey, go grab that mineral. So it's learning that doing nothing isn't a very good option in this situation. So that reward is constantly getting negative 0.1, 0.1, 0.1 for that no-op action. And then finally it's like, oh, okay, go grab that. And then this was after only like 20 episodes, you could see it was starting to figure out that the goal is to grab minerals. So there's some small indecision, but it's starting to get better there. And then sometimes it gets really close to mineral, but then it might enter like an exploratory mode. So it's still trying to figure out like all those values of when to perform what. So games in that time period where the first one we showed, it collected like 3 minerals, this one collected 39. And it kind of, it has stalling and it has indecision in both of these. So there's a stall, then it has indecision, but it's fine when they figure out, okay, there's some big indecision. And our goal is to obviously have that all disappear.
Right, so here's looking at our results. It's a huge, bit of a mess. This results of playing 8,000 episodes. So as you saw before, one of the videos was a single episode being played. And so there's a large number of factors as to why it wasn't necessarily playing optimally. One of the big factors probably was enough time. Maybe our model wasn't robust enough to, deal with finding the optimal solution, or maybe I think another potential issue is the fact that the maps are random too, and this is just the way that they designed it, right? It makes sense to kind of give it the AI fresh data, but it was a little bit more challenging for it to kind of reset and have a new sort of different configuration, have to learn from that. But again, that's the goal. And again, I think to point out, this is a very slow process. To do 8,000 episodes took about, I think, 2-3 days. It was like 3 days.
70 hours. Yeah, it's 3
Yes.
days.
Yeah, 3 days to get 8,000 episodes. And if we compare results to DeepMind, how many of you are familiar with, have heard of DeepMind before? Okay, good number of, okay. So they actually released the PySC2 library, and with that they released results. And here's their result for the mineral collection minigame. And so one thing I want to clarify too, as you can see, the x-axis is a couple hundred million, right? Well, these are game steps. But even if you were to calculate how many game steps we ran in total, so each episode has approximately 480 game steps. If you were to calculate how many game steps we took for our 8,000 episodes, that'll only be about 3 million, or about 4 million episodes, which would put you somewhere right around here, right? So they ran, in total, if you calculate this out, it'd be about over 1 million episodes. So they did a lot of number crunching, they ran a lot of experiments, and this would have taken about 78 days for us. So if we had, more advanced, hardware, a lot better hardware, we could do this a lot quicker. Another thing to keep in mind, they're using a lot. Obviously, they're a bigger research institution, a private research institution, and they have a lot of access to great minds and a lot of experience, and they're using a lot more robust algorithms, right? And so, one of the things that when you're looking at the paper that they were using that I think would be really cool if we could implement this down the road is they use recurrent neural networks, right? So we use a convolutional neural network, and they did too, right? So there's multiple layers to this, but we use a convolutional neural network, which is good for extracting features on images, so it's really good at processing image data, right? But they also use a recurrent neural network, specifically a long short-term neural network, or LSTM. And the benefit of this is that it kind of gets to keep track of it keeps track of a state. So it kind of, in every action, it has some sort of idea of things that has happened in the past, and it factors that in when it's computing the loss or updating the model. So it's not just looking at, okay, here's this last episode, how'd you do? Okay, here's the values you got, update the weights for the neural network. Whereas with LSTM, it's okay, here's the action of the trajectory, but here's the memory of our past experiences, and we can kind of base the update on these other past experiences as well. So again, there's some future stuff. And yeah,
Sure. For that though, it's also with this project, we would love to learn how to disable the GUI. So we feel there's a lot of time wasted loading up the GUI and then running it. And then also speed up the game clock, because we feel we could get a lot more episodes doing that. And additionally, we could containerize the project and then parallelize the training. So if we could get to a point where running, we calculate out we could run something like 600 episodes a minute, which would take 12 minutes for us to run our whole project, or 70 hours. Which that in itself is a lot of work to do. That's stuff we're not trained to do, we're just learning how to do an AI. But we're assuming that's what DeepMind, those are some of the techniques they were using to get to something like, almost 1 billion game steps. So an AI like this does have some real world applicability. It's essentially solving the traveling salesman problem, which can be used for mail delivery, power distribution. Also like the Roomba, that kind of thing, which we our example before, can be used. But there's more interesting like things you could apply to, like finding faults in a bridge, or like people trapped in an avalanche, are things that you wouldn't think about, because usually you go to like, oh, let's find landmines, or like you try to weaponize an AI. Like that's actually like a natural process that I believe people have. But you know, this could be used for good to like check construction work or check, you know, faults in a bridge. It's huge, especially in Minnesota. We've been doing that a lot for the last decade. So there's definitely like this AI is applicable to stuff in the real world.
So the nice thing about this environment is the customizability of like the game itself. You can add elements more to the game. Like resources can be added. You can add like obstacles for the AI to deal with. Like you can add walls, buildings, things like enemies. If you do a weaponized AI, you can add enemies to dodge. And for a bridge, you can add like collapsible structures within the game itself, so you can test where the bridge might collapse and see how the AI would react to like the change in the environment. So as it reloads the map each time, it can like learn from like these different blocks of how to bridge.
And then never mind. I think I'll set that one slide we kept going. The last slide basically just had a link to the GitHub repository if anyone's interested in looking at the code and playing with themselves, using it themselves. But again, if you're interested, we can talk after. Send you a link. But yeah, thank you everyone for listening to our presentation. And yeah.
Thank you.